Alright, so as you remember from the past couple of days, we've been going through the 5 basic categories of chemical reactions, and today I'm going to cover the 5th one. But before I do that, I want to make sure you guys remember what we've been doing, hopefully, for the first 4 types of reactions. So I have them written up here, the chemical reactions equations on the board, so let's see if anybody can remember what those 4 are. So who can tell me what the first one up here is showing? Yes?
Combination.
Very good. So you have 2 elements, or an element and a compound, that come together in the reaction to form a compound. How about the second one? Matt.
Decomposition.
Very good. So we have a compound that then breaks into its separate parts. And the third one?
Single displacement.
Good. Single displacement. So here you can see that whatever element B will then switch to the other element and create new compounds and elements in our products. And the last one?
Double replacement.
Double replacement, very good. So we have 2 compounds, they just switch partners, and we get 2 different compounds on the product side. Great, you were paying attention, excellent. Well, so for today I'm going to go through the 5th and final category of chemical reactions, and this is known as combustion. So, who's heard of combustion before? Okay, can anyone give me an example of where combustion occurs or anything like that?
An engine.
Good, combustion engine, that's a great example, and that's actually kind of what I'm going to be showing you today. Anywhere else that you know of combustion? There's one pretty famous disaster where this happened.
Nuclear?
Hindenburg.
Hindenburg. So think about that. Think about fire, big explosion, things like that. So that's basically combustion. But what I'm going to do to really introduce this to you today before we get into really any work on your own is I'm going to do a demonstration to show you combustion. Excuse me. So while I'm setting this up, I'm going to give you just a little bit of an idea of what is going to be happening. And then once I do the demonstration, I'm going to ask you guys to really observe and see what happens, and then kind of report back to me afterwards and let me know what you saw or heard or anything like that. So the definition of combustion is that we have an organic compound when mixed with oxygen. When we burn these 2 together, they produce energy in the form of both heat and light. So, going back to our chemical equations that we were just going through for the first 4 categories, this is a basic chemical equation for combustion. So what we have is X, which is typically an organic compound, which combines with oxygen, or O2, and it produces energy and heat and light, and actually creates 2 very well-known products. So what are these 2 products?
Carbon monoxide and water.
Very good. So that is basically what happens when we have combustion. So it's very simple, like the other ones, just a little bit more specific. So what I'm doing now to show you for this demonstration is that I am taking an empty water bottle, which should be filled with air, which hopefully contains oxygen, and I am coating it right now with an organic compound or an alcohol. In this case, I'm using isopropanol, or just basic rubbing alcohol. So I'm coating the inside of this, hopefully pretty well. And then I'm just going to light it on fire, and we're going to see what happens when it burns. And again, once I do this, I'm going to ask you guys if you can really try and observe what's happening and then report back to me so that we can talk about whether or not this reaction actually happens, if we can see any parts of the reaction, and things like that. So, once I get this set up here, I'm going to ask Christine to turn off the lights in just a second. Because what fun is a big fire if you can't see it. Alright, so for safety, just to give you guys a heads up, you're far enough away that you're okay. This is just rubbing alcohol, so I don't need gloves, but goggles are always a good idea, and of course, a hair tie. I wouldn't want my head set on fire, would we? Although that would be a really cool demonstration. Hairspray is very flammable, remember that. Alrighty. Lights. Oh, please. And can we get the back ones too? Oh, sorry. There we go. Okay. We got it. Alright guys, let's see if we can get this reaction to work. Lights back on, please. Ooh, well that was fun. I think we should do that again. What do you think? Yeah? Okay, well while I'm setting this back up again, who can tell me what happened? What did you see? Is there, any evidence that anything happened? Was there a chemical reaction?
There was blue fire.
Blue fire, good. And can anyone see what's in this?
Dust.
Water.
Ah,
Oh.
how do you know that's water? I mean, I put alcohol in it.
Yeah, it could be alcohol.
Could be alcohol.
Should try it.
I wouldn't recommend trying it for a number of reasons. First of all, we never drink anything we do in chemistry. But before I did the experiment, what did I do with the excess alcohol that was in here?
Poured it out.
I dumped it out. So do you think that much alcohol could be in here? Good. So what somebody mentioned before, we thought, well, maybe just something went wrong or we just had extra alcohol. Someone mentioned water. So now this would make sense. That is a product of a combustion reaction. What else we saw? We saw blue fire. There was water in the bottom of it. What else happened? What else did you observe?
Started slowly and then got bigger.
It did. It started slowly and then got bigger. Do you have any guess to why that happened?
More of the molecules are not changing.
Maybe. That's a great guess. And in order for those molecules to change, and that actually is a good part of it, in order for those molecules to change, you need more molecules to start with. And so if you look at the shape of this bottle, and you think about what components are actually reacting together, would it make sense that it's smaller at the top and bigger at the bottom?
There's more oxygen in the bottle.
Exactly. So there's more oxygen in the tube than there is just in the lips of the bottle. So, all right. Let's just do it one more time because this is really fun. All right. So make sure you really watch and see what's going on, and then again, we'll talk about it afterwards. Oh, if I can get my camera moving. All right. Any guesses why that's not lighting?
Maybe it didn't coat the top.
Maybe they coat the top. All right, well, let's try that. Let's just coat the top. I can turn the lights on so you guys can see that I'm coating the top. All right, so I'm going to just take whatever's left and I'm going to rub it around the top. Really get it coated really well, and then we'll see if we can get this to go. All right. So that's pretty well coated, as you can see by my hands. All right, lights one more time. Yep. Thanks so much, Christine. All right, ready?
No more oxygen in the bottle, maybe?
Very good. So now why would it light, go ahead and keep the lights again. Why would it light on top and not have that great huge all the way through the bottle? Ozzy?
There's no more oxygen left in the bottle after the first reaction. You converted it all to carbon dioxide.
Very good. So this was just an example, therefore, of both of the products we were supposed to get, right? So obviously the first time we had a little liquid in it. We had a good guess that that was water. There are ways that we can test to make sure it was water, and I just didn't put way too much alcohol in the container. But then the second part is, how do we know that there was carbon dioxide in the reaction? How do we know that that was a product? Well, can we see carbon dioxide? Not at all. So by doing the second test and seeing that it's not lighting throughout the bottle, we can make a guess that there's something that displaced the oxygen that was originally in there. So that would be our carbon dioxide. Now, why would it light at the top then?
Because there's oxygen in the air.
Very good. So now we're getting just that kind of reaction in the middle, or up towards the top here where our oxygen is actually taking place. What else did you notice about that particular example, or that time around, that was different than the first time? So we saw flame. We saw that there was a different size of flame. What about the color of flame?
It wasn't as blue.
Wasn't as blue? Was it still blue?
Yeah.
Okay. Was there any other color in it? So, good, so we had some orange too. Now, was that different than the first one? Was there both blue and orange in the first one? There were. So we can still guess that what's being lit, or what our elements are in this particular demonstration, are the same because they have the same color of light. So this is something we did in a lab earlier this semester, you'll remember, where the color of the flame when you are burning things can also help determine what the material is. So we know that we're still burning our same material, but as Ozzy pointed out, the fact that it's just at the top could be an example, or giving us a conclusion that we had carbon dioxide in the jug itself. Now that we've had this really fun, oh, okay, we're good, because I was about to get into the boring stuff